Welcome to this lecture on linear programming. Today, we are going to explore a fascinating technique called the Big M method. Imagine you are trying to navigate a complex maze, but you are dropped completely outside the maze walls. You need a temporary fake door just to get inside and start looking for the real path. This is exactly what the Big M method does for mathematical optimization. Let us dive in and see how it works. Now that we have our maze analogy, let us understand what this means mathematically. The Big M method is a specialized variant of the simplex algorithm. We use it when a linear programming problem lacks an obvious starting point or an initial basic feasible solution. Standard slack variables work fine for less than constraints, but when we face greater than or strict equality constraints, we are stuck outside the maze. To fix this, we introduce what we call artificial variables. These create a temporary starting point. But to ensure these fake variables do not ruin our final real solution, we assign them an overwhelmingly large penalty coefficient, denoted by the letter m. To see how we create this starting point, let us look at the math behind a standard constraint. When a constraint requires a minimum value, we first subtract a surplus variable, S1, to convert the inequality into an equation. However, if we set our main decision variables to 0, this leaves us with a negative surplus value, which violates linear programming rules. To fix this negative starting value problem, we add a brand new term, A1, the artificial variable. This variable has no physical meaning in the real world. It acts purely as a temporary bridge, creating a valid, positive starting point so the simplex algorithm can begin its step-by-step search. Now that we have a starting point, we must ensure the artificial variable does not stay in our solution. This formula shows how we alter the main objective function, z. The terms C1 and C2 represent the normal profit contributions of our real variables. The critical addition is the minus MA1 term. This acts as a devastating financial penalty. Because M is considered infinitely large, any positive value for A1 will destroy our profit. Therefore, as the optimization process runs, it will naturally force A1 to 0 as quickly as possible to maximize the overall value of Z. Before we move on to more theory, let us see this with a concrete example. We want to maximize a profit function Z equals 3x1 plus 5x2. We have two constraints. The first is a less than inequality. So we simply add a standard slack variable S1 to convert it into an equation. The second constraint is a greater than inequality. Here, we must subtract a surplus variable S2, representing the amount we exceed the minimum. But as we learned, this leaves us without a valid starting point. So, we add our artificial variable A1. This guarantees the math engine has a valid initial value to begin its calculations. Continuing with our example, we now modify our objective function. We add our slack and surplus variables with 0 profit, and we subtract m times A1 to apply our massive penalty. However, before we can put this into a simplex tableau, we must ensure the artificial variable does not appear in the objective function row with a non-zero coefficient. To do this, we take the equation from our second constraint and use basic algebra to isolate A1. We then substitute this entire expression back into our modified objective function. This crucial step links the penalty directly to the real decision variables. Let us finalize the setup for this maximization problem. By substituting the expression for A1, we expand the penalty term across the real variables. Grouping the terms together gives us our final objective, rho. Notice that the variable x2 now has a massive positive coefficient of 5 plus 2m. In a maximization problem, the simplex method always chooses the variable with the largest positive coefficient to enter the solution first. Therefore, the algorithm will immediately increase x2, which naturally forces the artificial variable out of the system, securing our real optimal solution. Now that we have successfully set up a maximization problem, let us look at how minimization differs. Minimization requires a slight adjustment to our penalty logic. When dealing with strict equality constraints, there is no unused capacity, so we do not need slack or surplus variables. However, we still lack a basic starting variable, so we must add an artificial variable. More importantly, because our goal is to minimize costs, subtracting a penalty would actually help the objective function, which is the opposite of what we want. Therefore, in minimization, we must add the infinitely large penalty m to the cost function. This brings us to the modified objective function for a minimization scenario. Here, z represents total costs. Notice that instead of subtracting the penalty, we are now adding m times a1 and m times a2. By adding an infinitely large number, we create a massive undesirable cost. The simplex algorithm is designed to find the lowest possible cost. Therefore, it will naturally seek to minimize this artificial inflation by driving both a1 and a2 down to zero as quickly as possible. This ensures the fake variables are eliminated from the final real-world solution. Let us apply this to a concrete minimization example. We want to minimize a cost function z equals 4x1 plus x2. Our first constraint is a strict equality. It requires exactly 3 units, so there is no surplus or slack. We simply add the artificial variable a1 to serve as our initial placeholder. The second constraint is a greater than inequality, requiring a minimum of 6 units. Just like before, we subtract a surplus variable s1 and then add a second artificial variable e2. This ensures both constraints have a valid starting variable for the initial mathematical matrix. Continuing with our minimization problem, we set up the objective function by adding the penalties ma1 and ma2. Just as before, we cannot leave these artificial variables in the objective function. We must express them in terms of our real decision variables. To do this efficiently, we add the two constraint equations together and use basic algebra to isolate the sum of a1 and a2 on the left side. We then take this entire algebraic expression and plug it into the objective function, replacing the artificial terms completely. Let us look at the final result of this substitution. By expanding the m penalty across the expression, we mathematically link the massive penalty to the real variables. This gives us a final simplified objective function, ready for the simplex tableau. In a minimization problem, the algorithm looks for the most negative coefficient to decide which variable to increase first. Because m is infinitely large, the term minus 7m is extremely negative, making x1 the most attractive choice. By bringing x1 into the solution, the algorithm will rapidly slash the massive 9m penalty. To truly understand what we just calculated, let us look at this visually. On this graph, the green shaded area represents the valid, feasible region where our real solution must live. However, because of our greater than constraints, we started at the origin, marked by the red dot. This is our artificial starting point, and it is completely invalid in the real world. The thick red arrow represents the big M penalty in action. Because the penalty is so mathematically terrifying, it acts as a massive force, driving the algorithm away from the origin and pushing it directly into the first valid solution on the edge of the green region. Now that we have seen the math and the geometry, why does this matter in practice? The Big M method is absolutely crucial because real-world problems rarely start with a perfect, ready-to-use mathematical setup. In industries like manufacturing, logistics, or diet planning, constraints often dictate strict minimum requirements, like producing at least 500 units or exact mixtures requiring exactly 50 kilograms of raw material. Without the Big M method, computer algorithms would simply crash or fail to start because they wouldn't know where to begin searching. The penalty gives the computer a strong incentive to find a valid solution fast. Let us summarize the key takeaways from our exploration of the Big M method. First, it is a clever mathematical trick designed to force a starting point in linear programming problems that do not naturally have one. Second, we achieve this by adding artificial variables, which act as temporary bridges to get the algorithm moving. Finally, by attaching a massive penalty m to these variables in the objective function, we guarantee the optimization process will eliminate them, leaving us with the true, optimal, real-world solution. You now have a solid understanding of how to handle complex constraints in linear programming.